Hello, grade 9s. I hope that you guys are having a wonderful day. Today we're going to talk about house wiring and power and how that all comes into play. We've been talking a lot about circuits, things that we can make with circuits, but realistically the most important thing to us is how we use that power in our houses and where we get it from and how we pay for it. Because unfortunately, as in everything in life, we have to pay for the power that we use. So that's what we're going to talk about today. So the first thing that I want to start with is meter, fuse, and house. At the top of the page, you guys can see. So you guys don't have to write the notes today. You guys can just cut this out, paste it in your notebook. You get a little bit of break from the notes, which some of you guys might like. So the first thing is the electricity comes through power lines. So these are coming from whatever source of electricity the town or province that you are living in is using. So in places like BC and Ontario, they're probably using more hydropower, whereas here we're using coal-generated electricity. So the power is coming from that power source, traveling through power lines for kilometers on end, which you guys see the power lines when you drive across the roads. Eventually, when it gets to your house, it has to pass through a meter. This meter is located generally by a garage or outside of your house. You can see it physically. It's about 1 foot off of the ground, just like a little box. And there's a number on it. The reason that there's a meter is so that the power company can record how much electricity you are using so that they know how much to charge you. Pretty straightforward. Once the electricity passes through the meter, it's going to go through a fuse box, which you might have a few of these located around your house, depending how big it is. Some houses only have one, some might have 2 or 3, all depending. So this fuse box has a bunch of fuses, and remember we talked about the role of a fuse is to protect against power surges. So to make sure that your house is protected so that you don't have an electricity fire. So these fuse boxes will have a fuse for every circuit in your house. So depending on the electrician, they will decide when they wire your house how many circuits, what rooms have circuits that are connecting to each other, and so on. Your kitchen probably has more fuses than any room in your house just because you have quite a few things being plugged in and using electricity, and we want to make sure that your house can handle it. So the fuse box has all the circuits in your house, and if something happens and you have a power surge or you're using too much electricity and it's trying to protect it, the fuse will go off and then you'll have to restart the fuse again. Then once the electricity passes through the fuse box, it's going to go into your house and then it's going to do whatever it needs to do. Inside of your house, there are 3 different types of wires that you'd see. The first 2 are called the neutral and the hot wire. These are both live wire, which means that the current is flowing through them. The neutral wire is white, hot wire is black, and they're both insulated so that if you touch them, then you're not going to get an electric shock from that. These wires together form the circuit, so a full circuit. So they're taking electricity to and from the devices that you're using. The third wire is really, really important. It's called the ground wire. So this does carry an electric current through it. Its main role is to channel any leaked current to the ground so that you're not getting shocked every time you touch a device or something inside of your house. So the ground wire has a very important role for that purpose. So you guys understand a little bit about how your house is wired, all the different things that the electricity has to pass through. Now we're going to talk about power. So this is unfortunately another calculation, which some of you guys really like and some of you guys don't. You don't need to fear. It's not a hard formula. There's actually 2 that are kind of connected. All we have to do is just learn the new variables and learn the new units, and we'll practice the formula together a few times. So don't fear, okay? So the new variable that we're going to be solving for, it's a little bit different from Ohm's law. We're going to be talking about power. So power is measured in watts. You guys have seen this every time you buy a light bulb, anything like that inside of your house. It says like 100 watts or 60 watts, something like that. So that's what we're calculating in this example. What power actually is how fast a device is converting energy from one form to another. So you guys remember, we talked a lot about energy transformations last week. I had you guys looking, we talked about electricity to heat, electricity to light, we talked about the piezoelectric effect, we talked about solar, all of those different energy conversions. So we want to figure out how fast those transformations are occurring. So it does have a little bit kind of going on to efficiency in that way, because we're looking at how good it is at converting that electricity. So the two variables that we need to find power are current and voltage, which we just used in Ohm's law. Remember, current is using the variable I, which is measured in amps. Voltage is V, measured in volts. So those are the two variables. All we have to do is multiply them together if we're finding power. It's when we're solving for current and voltage where that formula becomes a little bit different. And I'll show you the other two versions of that formula when we do some examples. The last formula, still talking about power, is looking at power, time, and energy. It's useful for us to try to solve for energy when we're looking at how much energy we're actually using, because power is different from energy. Remember, energy is measured in joules. So the one thing that I'm noticing right now on this piece of paper is that it doesn't actually say that. So if you guys want to just quickly grab a pencil, something like that, and then right here where it says energy, energy is measured in joules. In case I didn't make that clear earlier. So energy is measured in joules. To calculate energy, all we're going to do is figure out the power and then multiply it by the time, because power is a rate and we're looking at how long it's taking to convert the energy. So if we kind of take energy out of that and use that in the calculation, we can find just how much energy we have in total. This right here, this kilowatt hour, you might have to calculate this. You'll do it in my practice work, but the PAT generally isn't always concerned with kilowatt hours. The significance here is that this is what you guys, your parents, would see on their power bill, a kilowatt hour. So, and we would look at different devices like dryers and washing machines and fridges. Any appliance in your house would have kilowatt hours located on them. So we can use this number to compare how efficient or how good a device is. So kilowatt hour is the total energy supplied to a 1,000 watt load in 1 hour. When you are doing or getting a power bill, to figure out how much your power bill is, they're going to take the kilowatts that are used from the meter in your house right here, obtained by the meter, and they would multiply it by whatever the rate that the power company has chosen, multiply those two numbers together, and then that's the number that would show up on your power bill. Now, I mentioned that some appliances have different kilowatt hours located on them that we could use. This is called an Energuide label. And I'll show you guys a picture of an Energuide label when I come back. But it's essentially a sticker, and you can look on any appliance in your house and you'll see this, that tells you the kilowatt hour. So you want to pick something that is relatively good, meaning it doesn't use as much electricity, because that will make your power bill cheaper. Hopefully this stuff that I've talked about makes sense to you guys. If you have questions, we can talk about them on Wednesday when I get back, okay? I'm going to stop the video portion here, and I'm going to flip the page, and we're going to do a few calculation examples together. So if you guys have a calculator, a pencil, I'm just going to flip the page and we'll do some examples with that. Some of them are easy and some of them are more difficult. So here is the foldable that Mrs. Choi should have handed out to you guys. You guys are going to cut this out along with the piece of paper that had the notes on it and glue those into your notebooks. So it says a household computer that remains on all day has a power rating of 100 watts when plugged into an outlet that draws 120 volts. What is the current flowing through the computer? So 100 watts, that's power. 120 volts, and then we're trying to solve for how much current. So before I get too far ahead of myself, I'm going to give you the 3 versions of this formula. You guys can write this down at the top. So the one from the notes that I gave you is P equals I times V. If you want to solve for voltage, it's going to be power divided by current. And if you want to find current, it's going to be power divided by voltage. So those are your 3 versions of the formula that we'll use to do this calculation. If you look at the first example, we list our variables like I asked you guys to do with Ohm's law. Power was 100 watts, current was 120 volts, and then, oops, I put that in the wrong one, grade 9s. Voltage is 120 volts, current is our unknown. Well, above, the formula that gives us current is this third one over here. So I'm going to write current equals power over voltage, substitute in my variables, 100 watts divided by 120 volts. If you put this in your calculator, you're going to get 0.833 amps. Please don't forget the units. That's very, very important to me, okay? The next question says a fridge with a freezer plugged into an American outlet draws 100 volts of electricity. If the current is 0.33 amps, what is the power rating of the fridge? So we have voltage, we have A, amps, that's current. What is the power rating? So P, I, and V. P is our unknown. Current is 0.33 amps. Voltage is 100. The formula from above, where we're solving for power, is this one over here, the first one. So P equals I times V. If we substitute those numbers in, current is 0.33 amps times our voltage, 100. You're going to get an answer of 33 watts. Again, please make sure that you include your number or your units. Very, very important. Power is in watts. That's the only new one so far. Next question. A rice cooker has a power rating of 495 watts while cooking the rice. If it draws a current of 4.12 amps, what is the voltage? So our variables P, I, and V. Power 495 watts. Current 4.12 amps. Voltage is our unknown. This is the last example where we have a new equation, or new version. So this is to solve for voltage. V equals P over I. Our power is 495. Our current is 4.12 amps. So if we divide these two numbers, 495 divided by 4.12, our voltage is going to be 120 volts. That's our final answer. So those are the 3 different versions of how to use that question. The very last example here, I know it says ABE, it should say ABC. It starts off very straightforward, but then it's asking us to do one last new thing. So this last question is what I would call a standard of excellence question. It's challenging, pushes you outside of the box. So if the first three made sense to you and this last one doesn't, that's okay. Don't panic, and we can practice this more when we get back. So 1.5 amps of current passes through a new color TV set, which is connected by a 110 volt outlet. How much power will the TV set use? So our formula for power is P equals I times V. P, so we have a current of 1.5 amps. Our voltage was 110 volts. We're solving for power. So we're taking, we are taking 1.5 amps, multiply it by 110 volts. Our power is 165 watts. We're going to use this number for part B, which says if the TV is operating an average of 6 hours every day for a week, how many kilowatt hours of energy will it use in 1 week and in 1 year? So the first thing we're going to do is figure out the kilowatt part. So this is new for you guys. There are 1,000 watts in 1 kilowatt. So the first thing that we have to do is take our 165 watts and get it into kilowatts. So if we divide this number by 1,000, that's going to give me 0.165 kilowatts. That's the first thing, okay? So just like if we were to take meters and put it into kilometers, I am taking watts and putting it into kilowatts. We do this by dividing it by 1,000. Now, we're going to figure out the kilowatt hours by multiplying it by how many hours, which in the question is 6. So 0.165 kilowatts times 6 hours gives you 0.99 kilowatt hours. That's the first part of the question. So it says, how many kilowatt hours of energy will it use in 1 week and in 1 year? So we're going to do this by multiplying it by a week and a year. So let's start with a week. There are 7 days in a week. So we're going to times it by 7. So that'll give me 6.93 kilowatt hours per week. And if we multiply it by 365, that's how many days are in a year. We're going to get 361.35 kilowatt hours per year. So all I did was times the kilowatt hours. So that's looking at how many kilowatts it used per hour. And I figured out how many kilowatt hours per week and per year by multiplying it by how many days are in a week and how many days are in a year. Again, challenging question. There's a lot being asked there. The very last thing, it says, if electricity costs 12 cents for every kilowatt hour, what is the cost of operating this TV set for 1 year? So we're going to take the 361.35 kilowatt hours per year, and we're going to multiply it by the cost. The cost is 12 cents. Okay, I put it in a decimal because If we're doing any calculations, multiplying by 10 is going to give me some weird numbers. So make sure that if you have cents, you put them as a decimal. So if you multiply 361.35 times our 0.12, we're going to get $43.36. So that's how much it costs, which is very, very low. Probably because this question's made up. It's probably more expensive than that to run a TV. All right, grade 9s. So just to recap, these first 3 questions, so 1, 2, and 3, that's what your practice is going to be on for this week. So please work hard, do the practice work. If you have any questions, don't panic. We can address this on Wednesday when I'm back. Have a great day, grade 9s. I miss you very, very, very much. Bye.